Okay, so we're going to solve problem 1 numerically using the shooting method and Runge-Kutta fourth order. So problem 1, that's already on YouTube, so you've seen that, and this is the differential equation that comes from it. So it's a second order nonlinear non-homogeneous ordinary differential equation. And because it's a second order, we have two boundary conditions. If we want to use Runge-Kutta, though, we have to change from having a boundary value problem to an initial value problem, meaning that instead of having two boundaries, we're going to have the initial, value and the initial slope. So that just means that we're going to be solving it, and now rho, which was our position, we're going to treat it as time, and we're going to say that time runs from 0 to 1, whereas before we had position from 0 to 1. This is our differential equation, which I just took the non-homogeneous term over to the right-hand side. That is our initial condition, and then we need to know what the slope is at 0, the initial slope. And we don't know what it is, therefore we're going to guess some value, which I'm going to call beta. And this is our shooting parameter. So we're basically guessing the trajectory, the initial trajectory, and then after we solve the problem, we're going to go back and check if that value of beta gives us the boundary value that we wanted. So this is a means to iteratively solve this problem. So that's part of the issue, and the other part of the issue is that in order to use Runge-Kutta, we have to be in dealing with a first order problem, and this is a second order. So we have to convert a second order ODE into two first orders, and we're going to do that by transforming from U to V1 and V2, where V1 is just U, and V2 is the derivative of U with respect to rho. And when we do that, we get the derivative of U with respect to rho is equal to V2, because that's just the definition. And then we get the derivative of V2, which is the second derivative of U, is equal to our non-homogeneous part. And then we have our initial conditions, that V1 at 0 is equal to 0 and V2 at 0 is equal to beta. And now we have a set of first order ordinary differential equations that we can solve. And we're going to take this and we're going to rewrite it in matrix form like this. So the left hand side are derivatives, so we get derivative with respect to rho of V1 and V2 is equal to V2 and then this non-homogeneous term, which is our new V1 kappa plus V1 over rho. Great, that's what we want. A second. That's what we want, and it's what we need in order to be able to solve the Runge-Kutta fourth order. And there are several different ways that you can look this up. The method that I found, or the write-up I found, is this one, which is just online. This was in Math Stacks Exchange, but these are in lots of different textbooks. And excuse me, this version uses a expression for f and g on for the set of differential equations. So I decided that I would write out mine in terms of f and g, so I can just follow the numerics in the example. And Runge-Kutta is basically just a little algorithm that you step through to get a solution. So ultimately, though, there's going to be a problem here, and this problem has to do with the fact that we've got all of these 1 over rho in here, right? here in the right-hand side of our expression. And the reason that's a problem is because if you look here at this first term, so basically in Runge-Kutta you are solving for a set of 4 parameters, 1, which in this one they're calling it k, 0, 1, 2, 3, and the second parameter, which we call L, 0, 1, 2, 3. Oops, not there, I guess. It's here. We have a expression that is going to require us to know what's happening to rho, or what's happening in the limit the rho goes to 0, because we're on the initial side of the problem, for the right-hand side of our problem. And if we look at it, we got, I took the rho out from under here, and I put it in front of kappa and in front of the top, just rearranging it. But you wind up with getting a rho here and a rho here. And you get a expression that is 0 over 0. So when you're taking this type of limit and you get a 0 over 0, or you get a infinity over infinity, you can use L'Hopital's rule to decide what to do. And here we are. So having L'Hopital's rule, L'Hopital's rule says that if you take the limit and you get a 0 over 0, then the limit is instead determined by taking the limit of the derivatives. And if we take the limit of the derivatives, taking the derivative of the top gives us nu v1 plus rho v1 prime rho, and then the bottom we get kappa v1 prime rho. Well, that's 0, that's 0, and this is a finite value. This is just a parameter, right? So whatever, like 5, well, okay, 5 times 10 to the minus 5, but it's a parameter. And this is also going to be a non-zero generally, which means these are non-zero, this is 0, and we get 0. So what that means is that in the limit the rho goes to 0, this g goes to 0, and that's going to be come in here to the value of L that is being used. And if we do this, now we immediately have a value we can use for that L0, and we can solve the problem. So let me show you that. If I can